Hello, everyone. We are on um, low volume analysis and slash system, I guess. Or I guess analysis would be better. A system. Oh, it's analysis, right? Okay. So the major formula that you're gonna want to know is pH, energy going, energy two, energy one, is equivalent to P two, N two, minus equal to heat transfer. This is velocity. Oops. This is velocity, and this is energy for the system. The C is also height. It's going to be our height. And then the way I like to look at it is this is kind of its own thing in comparison to the entirety of the formula. So this is M out, which is equivalent to this. So HA velocity. Let's see. Out. All this is kind of out. So this is pretty much the main formula you want to know. There's also, you're probably wondering, what is this? What is that technically? That you almost, if it's a steady state, steady flow problem, this will mostly, it'll be like a rate. State flow, and this is going to be 0. And this is equivalent to E to M2 minus E1 M1. But if we are given things for the system, because this is the system, if I'm not mistaken. And then this is like, we're dealing with like the liquid and out of the system. But when dealing with E, our E is going to be equal to pretty much U plus potential energy plus kinetic energy. And the formulas for potential energy and kinetic energy are the same. The only difference is this internal energy. But the way I like to look at it best, so this is like, you're probably wondering, like, what is potential energy and kinetic energy? How is this different from this? But this is more or less like, say your system, which is having M initial and then M out. Say the system is, I don't know, rising in the air for some reason. That change is your potential energy. However, because you have treated this whole thing as a system. So like if the entire tank, if you will, including like the water, the entire tank itself is going and rising up in the air for some reason, then this would be potential energy. Or if it's like for some reason the entire tank is going really fast. However, when say this is like a pipe and this is grass, some nice grass, the liquid or the gas is traveling and now it's at a different height. It's either going to be liquid or gas or something. It depends. Almost it's never like a solid, but it's normally liquid or gas going through the pipe. And so now the liquid is at a different height. Now, so that's when we would have a difference in potential energy. And this pipe is grounded at the grass. However, if the entire pipe, say our entire system, the pipe, just randomly started rising, then it would be potential energy for this. So I hope that makes sense. So I'm going to erase this and kind of explain more of what M2 and M1 are for this problem. So essentially say you only have M initial. There would be no ME. We're not talking, there would be nothing going in. So your ME would be 0. Or like this part of the equation would be 0. This entire thing would be 0. But the point I'm getting at is there's going to be an M1 here, like an amount of liquid initially. And there's going to be an M going into the system. And then this process at like a certain time, it's going to be more fuller. It's going to be higher up, and I guess the gas will be higher, or it'll have more gas in it. So the M2 will be different. However, if we have the rate at which M initial or M initial is going in, the same rate M initial is going out of ME. Does that make sense? So the rate at which this liquid or gas is going into the system is the same rate that it's exiting, so that these two equal each other. And this is what we call a steady state problem. because the rate at which this liquid is going into the system is the same rate that it's leaving the system. And therefore, the amount, like the amount initial is equal to the amount final that's in the system. It's water. That makes sense? So they equal each other. So you're left with a problem. We're talking about rates again. You're left with a problem that looks more like this. Due to this M initial equaling ME, you can just put M. They all equal each other. And then you can do H initial minus H E. It just kind of depends on the format, but pretty much you're just going to be subtracting everything. Right. Be initial, and then this would be exit. Initial. Or you're going out. And that's kind of how my best explanation. But let us go to a problem where we are dealing with something a little bit more. Say you have something. Let's say you have just something exiting. That means there's no initial, and then this ends up being zero. This portion. Just a heads up. But the question is, what do you do when you have a lot of systems? Say you only have one thing going out, but now you have two things. At M2 and M3, you could consider this M2 plus M3 would equal M exit. And then this would be M initial. So now we know that M, which is also equivalent to M1. That's a really good, helpful way to just understand it too. Also, if this is adiabatic and there's no work, you can set M initial, and that's how it works. But I hope that was helpful. Kind of a short video, but I hope it was helpful, and have a good one.